In this episode, we sit down with Ash Vardanian, the founder of Unum. We talk about his suite of open source tools like usearch, a search and clustering engine for vectors and texts.
Oftentimes software is only capable of taking advantage of 10% of the hardware it's running on. Piece by piece, library by library, I'm open sourcing a lot of really cool data processing tools to process more data, which seems to be like a really important thing in the age of AI.
We also talk about the implications of his tools being smaller, faster, and more efficient.
I think the implications are on two ends. And so the most obvious one, if you are more efficient, you can do the same with less. I'm more excited about the other end of things. So you still pay the same amount of money for your hardware. How much bigger can you go?
And how he thinks about accessibility for developers and their end users.
I think it's an important point, like making sure your libraries are portable. A lot of the companies that we see these days only take one single compiler or one single target platform. They say, let's say, we only run on Intel CPUs, or we only run on ARM CPUs. We only work on this operating system, which is fine. But in our case, we built something that is like lower level, so it must be accessible to a lot of different users.
Let's get started. Welcome, Ash. You're working on Unum. I would love for you to talk a little bit more about exactly what you're building and why you decided to work on it.
Well, glad to be here. And as for Unum, it's a software foundation thing. I spent 8 years designing some really interesting technologies around data processing, with the overall thesis being that modern hardware is much more capable than modern software. And by much more, I mean, oftentimes software is only capable of taking advantage of 10% of the hardware it's running on. So I decided to change all of that. And piece by piece, library by library, I'm open sourcing a lot of really cool data processing tools, all under Apache 2.0 license that you can go and use in your own projects to process more data, which seems to be like a really important thing in the age of AI.
So within this, you've got a bunch of things, right? You've got uform, you've got usearch, you've got Stringzilla. How do you determine what to work on specifically within these things?
All of those things are related. It's a bit of an incremental process by now. Once you've defined the core libraries and the directions that you're taking, which part of the stack are the slowest and require the most effort, like to rebuild, it becomes like an iterative process. So you start with uform. Uform, for those not familiar, is our family of pre-trained neural networks. So we train our own models, mostly around the topic of multimodal understanding. So a lot of companies either tune models or train their own models. Most of the time that was like text-only stuff. So you would train an encoder architecture like BERT for mask language modeling. You would train a GPT around like causal LM or just normal LM stuff. But we've noticed that there is going to be like a lot of issues when people start shifting from text only to foundational models that is related to the ability of a neural network to understand content of different modality. So we've spent a few years actually understanding the ways we can synchronize many different transformers or layers of the same neural network itself to be able to understand and properly map both images and text into the same high dimensional space where it can compare both in terms of similarity. That's uform. Usearch is quite different. So it's not on the AI training side, it's more on the AI infra side. So vector search is like a very popular topic these days. Feels like everyone needs it in their application. And I couldn't be more passionate about it. I've designed 15 vector search engines probably during my career. And when I was forming the first teams a few years ago, we actually had one of the interview questions as to implement a k-approximate nearest neighbor search structure, given some of the existing HNSW implementations or locality sensitive hashing or the other stuff like this. So this year, when it suddenly became so popular, I decided that the world needs at least one really portable, but still efficient implementation. And after years of practice, it didn't take much time to design a fairly short solution in just a few thousand lines of C++11 code, which makes it super portable. I managed to wrap it into bindings for temp programming languages, which might be more than every other system of equal nature combined. So, and this is not just like an API call to a server that runs somewhere else. This is actually an embedded library. So the same code base is used within Swift applications on mobile. It's used within C# applications on, let's say, Windows systems and within .NET environments. And the same system also powers some of the largest servers in the world, as well as search functionality within multiple database companies. And the last but not the least, Stringzilla. So we've mentioned only three of maybe 10-ish libraries that I have. Stringzilla is a bit of a tangent here. And I guess you can guess from a funny name. It's not directly part of Unum, at least as of right now. It started as just a short code snippet that I prepared for a conference a few years ago to make a point. And the point aged well. It's still relevant today about how substring search can be efficiently optimized, even compared to libc, which is probably like the most deployed library out there. So it must be very optimized. It's the foundation of any C, C++, or even programs written in higher level languages. And I managed to accelerate the average case by a factor of 5 or 6. The worst case didn't get much better, of different substring operations. And this is such a low level thing. Every application has a strings class. And if you can make strings across every programming language, across every application 6 times faster, you're actually like shaving off some noticeable energy consumption from every single data center around the globe. So no one cared about it for a few years. And then this year it suddenly became somewhat popular. And I decided to wrap it into a Python library. So now there is one more project under our umbrella.
Nice.
How do
So
you go about how do you go about finding these sort of opportunities? Like you said, no one really cared about vector search for a long time. You were working on it for 15, you built 15 different vector engines. And then Stringzilla, again, there's not that many people thinking about this low level of optimization beyond like high performance compute, research groups and that sort of thing. So like, how did you get into this? Why is this something you're passionate about?
I think I was always, uh, like at the first place, I was focused like on the final product. So I started programming about 20 years ago. And in the very beginning, I was very far from high performance computing. So I've heard and learned the languages like C, which are obviously predating me and my software career. But when I built those apps, I always wanted to make them smarter, more scalable, analyze more data. And at some point, I noticed that all the apps that I built share the same core functionality for data processing and content understanding. And I thought, wow, instead of building like a dozen apps, I would rather focus on building one framework that would help not just me, but other people down the road. Hence the name Unum. Unum in Latin means one. So just one framework for me and for everyone else who wants to build really smart applications and deploy them everywhere. And then by that time, I was doing astrophysics. And even though I love theoretical physics, but I had to do some applied stuff. And I had an assignment to actually optimize some of the kernels for numerical simulations running on a cluster. And my professor at the time suggested me to use Root, which is a big framework written at CERN. And then some of the other libraries and some of the other kernels had to be written in Fortran, which I really disliked. Uh, if you are a developer, you probably understand Fortran.
Yes.
Maybe not the sexiest tool out there these days. It's the first high level programming language. That's how old it is. So, because I didn't want to comply, I actually went back to the drawing board and I rewrote all the libraries, porting them to GPUs. And it was around 2012. So, like the early days of GPU stuff. Obviously, my simulations on even on a laptop GPU went faster than on the entire CPU cluster. So from this point on, I knew I have an advantage in high performance computing. So it's like, once the question was, should I build a framework for large scale data processing? I knew the answer is yes. And I knew I should take this high performance computing approach towards optimizing all the bottom pieces of infrastructure so that every other application can benefit from it.
When you've been talking about Unum as a whole, you've also mentioned like wrapping it in, uh, wrapping it such that other people can use it. And also, when I looked at what was it, I think it was Uform. You also made sure that it was in different languages, not just English, when you chose the data set. It seems like even though you're focused very much on low level infra, you think deeply about the applications or the ways that people can use it and making that simple and easy to use. Is that true? And if so, why?
So, of course, I want it to be true. Some of the first successful projects that I've ever made were in edtech space, and they were like consumer applications. So I had to understand the way people would study on mobile phones. And those were the early days of the iOS App Store. So all the design patterns for apps that we take for granted today, they were laid in stone around 2009, 2010. And you had to invent every single piece of UI and imagine the way people would interact with the application. Now that I'm like so many levels down and like close to hardware, bare metal stuff, I still have to like think about the end consumer and the developers who are going to build products. So, and that's actually uh, very important for anyone kind of probably be building infra. And I noticed that being at, let's say in San Francisco, I get to meet a lot of builders, which is amazing. So like my feedback loop is almost immediate. Every day I see some guys using my libraries for specific kind of data processing, and they always have feedback for me. Of course, you start prioritizing because your resources are not infinite. But as you mentioned, in some cases, you do this even for like use cases that are a bit further from yourself. So Uform, the neural networks, we've made sure that they perform almost equally well in 21 different languages. So myself and my team would have an international background. We're not born or raised in the US or any English speaking country, but people who were kind of born and raised in those countries have a lot of advantage in terms of the tooling and even the AI models that are being released these days, because their English capabilities are far beyond their multilingual capabilities, especially the open source models, especially in multimodal setting. One of the reasons for this is that people use public data sets like Common Crawl, which is not balanced in any way. Common Crawl is mostly English content. Over half of it is English. Roughly 6% of it is Russian. And every subsequent language is less and less represented. In our case, we first tried a few different low resource languages, and assuming our Armenian roots, we wanted to try Armenian. We also tried Hebrew as another fairly low resource language, also from the Middle East. But what we've noticed is that the accuracy of our models trained on a balanced data set with equal amount of every language becomes better, not just in those low resource languages, but sometimes in some of the most popular languages out there, primarily Hindi and Arabic. So comparing to even larger open clip models for multimodal understanding and retrieval, that also produce embeddings that are 3 times larger and heavier than ours, we still got better recall at 1 on retrieval and search tasks. And for Hindi and Arabic, our boost was by 10 points, which is huge. It's unseen. So sometimes you can get a lot of advantage from just understanding that the world is like not uniform. Not everyone speaks the same language, and just tuning for every kind of region, making sure that everyone gets the best in front.
Talking about accessibility. So
Okay.
I think it's cool. There's kind of like not to get too far ahead of ourselves, but there's the focus on kind of accessibility to like the end user, but then also kind of at the technology level, right? Like the fact that usearch can be run on an iPhone or some sort of embedded device?
Yeah, I was up tonight and with one of the users and contributors of the project, we were trying to figure out the way for people to be able to build usearch for AWS Lambdas. So even in serverless applications, this native library with all kinds of hardware acceleration and assembly level tricks would be able to be like recompiled and reused for your like custom serverless environment, which I think is a very neat thing. So one step closer to running in a browser, but the browser makes a bit less sense because of like the memory constraints.
Would that only be because there'd be no persistent memory in the Lambda setting, is that right? So you could just throw in a Lambda, have it do some big calculation or, whatever, and then give you the result.
Yeah. The, so like usearch wraps a lot of different functionality, even like from the underlying SimSim. And let's say if you want to do exact search within a specific batch, you can still do it with usearch and it will like also be like hardware accelerated. So if let's say you have a Lambda that gets 1,000 vectors in and needs to shrink them down, compute the distances, you can do it with usearch.
So, so Ash, there's this focus on not just accessibility at the language level where you're making sure that different languages are equally represented in training set, but also at the engineering level and the infrastructure level where you have these kind of single header C files that can run anywhere, right? You can run on an iPhone, embedded, AWS Lambda, it sounds like, kind of anywhere that people would need to access them. So what is that kind of, or like, how do you think about that more generally?
Yeah, I think it's an important point, like making sure your libraries are portable. So a lot of the companies that we see these days only take one single compiler or one single target platform. They say, let's say, we only run on Intel CPUs or we only run on ARM CPUs. We only work on this operating system, which is fine. But in our case, we built something that is like lower level. So it must be accessible to a lot of different users. And this is not only true for C, but also like when we work with Python libraries and let's say UForm, the neural networks, the obvious thing would have been just to use the Hugging Face transformers and inject our code directly there. But it's not necessarily always as portable and stable as, let's say, doing a pure PyTorch model. So UForm comes with a PyTorch implementation rather than Hugging Face implementation. And then aside from this, we also ported our models to various interesting, unique kinds of hardware. So notably, most people either run on the CPU backend, the default one provided by, let's say, PyTorch, or CUDA, NVIDIA GPUs. All of those are great, excellent pieces of hardware, but there is more stuff on the market. So one of the interesting things we did recently with published inference code for GraphCore IPUs, which are like new chips, like kind of more neuromorphic. So they have less VRAM and more SRAM. SRAM is like the memory right on the CPU core or like IPU core in this case. And VRAM would be like the larger pool of external memory. But as you mentioned, yeah, like on the C side, this is much more pronounced. So with usearch, the library that we designed for vector search, we have bindings for Python, C99, JavaScript, Rust, Golang, Objective-C, Swift, C#, Voltron language, even though those are probably outdated a bit, and probably a few more other languages that I've forgotten about.
Earlier, you mentioned by being in San Francisco, you see a lot of builders and you get feedback really quickly. What are some interesting things that people have been building using the tools that you've created?
All kinds of stuff. So it ranges like from super small scale to extremely large scale. So on the super small scale, I see people running our stuff on tiny embedded devices. Also, like when they compile it to WebAssembly, they manage to run it on like stateless systems like Lambdas on AWS. Aside from this, there's a lot of innovation that's happening on extremely large scale. Of course, in many cases, those are the big tech companies So let's say if a major tech company is, let's say, training a new huge model, they would want to use some efficient libraries to process and clean up the data set, for example, or let's say adjust their training pipeline or even the inference pipeline. So let's say if you're using like a vector search system, you can use it on both sides. Like when you do training, you can use vector search to kind of sample batches in a non-uniform manner, kind of prioritizing some form of grouping them to kind of converge to better models sooner. On inference side, of course, everyone now knows what retrieval augmentation is, and being able to pull information from a neural network from external memory store, and then just prompt this into the neural network itself to kind of generate answers within a better context. But like the last couple of years, we gave a few talks around the topics of re- retrieval augmentation and the way this can be done not only at the prompt level, but also with custom models that can do like, let's say cross attention into the external memory pool. So that in that case, your vector search engine is actually becoming part of the architecture itself. So your neural network is trained to know that there's like always a memory pool outside that can treat it.
I think
Very
this is a
interesting.
perfect segue into another area that we want to talk about, or another theme of questions, which is you had this talk on a high level overview of the open source frameworks that are out there. And one thing that's been a huge, an acronym that people have used a lot over the past year in San Francisco is RAG, Retrieval Augmented Generation. And so I'm curious as to your thoughts on, I guess, how you see using external memory when actually creating these applications.
So I feel like this is the most natural thing ever. And for years, I was criticized for this. So I'm not the first one to suggest it from it. So if we look at the modern computer architecture, most people would classify it as a von Neumann architecture, which essentially means that the memory and logic are separate from each other, connected by different buses. So this idea of like separating memory and logic is not new in any form, especially to computing. And once people started working on neural networks, uh, people started asking the same question: wouldn't it make more sense for the language model to be actually a language model, just a language model? It doesn't have to be the knowledge model, the world model, the whatever database or data set that you query from. It's just a form of understanding how to model the language, similar to humans, and the information can come from somewhere else. So this is kind of what retrieval augmented generation would be. Like you gather information from somewhere else and you use the language model to kind of put it into concise form, understandable by any English speaker.
Yeah, and it seems, I mean, even, I think like a year ago when RAG became really popular, right? Like all these chat your data apps came out. They're all over Twitter. There's like a million different ones, chat YouTube, chat PDF. Um, it wasn't totally clear that that was going to be as big of a phenomenon as it has ended up being. And I think even the last week really punctuates that with OpenAI now releasing their own, you know, native memory to their LLM platform. How do you see this progressing with open source vector databases, open source models versus these kind of monolithic OpenAI APIs now, like their new assistance API that has memory baked in? You have things that like LangChain that kind of, connect all these different things together. Where do you think the state of all this is in I don't know, the next 24 months?
So I'm not sure if I'm the best person to answer to this question. So like I want just one tiny actor of this entire pool of technologies and uh, partly open source movement. So for many years, I didn't really understand like how open source works. I really loved the concept, but the first 7 years of working on Unum, I didn't think I was like mature enough to start open sourcing some of those pieces. Of course, I'm very thankful to the community for enjoying and appreciating the stuff that we release. And now every time you release something and you get the next dopamine boost from seeing people using it, you want to release more and more. So we definitely have a lot of technologies that I think would be useful in the upcoming race for AI, AGI, and better infrastructure, I tend to think that yeah, and Google and OpenAI have some amazing technologies for sure. But I also think there are like a number of teams around the globe, hopefully us included, that just have so much accumulated knowledge in the domain and maybe some weird technologies that will turn out to be like pivotal for the next big thing in AI that I'm kind of hopeful. So if we can onboard more people to kind of release their work and maybe find a good way to balance their effort with some form of, let's say, compensation where that effort would be sustainable because not everyone has the resources just like to keep releasing everything infinitely for many, many years, then open source AI movement is in good hands.
Yeah, I tend to agree with you. Kind of, short term, it looks like some of the big players are pretty far ahead, but the long arc of time may tell us something else eventually. We'll see.
What do you think about frameworks like LangChain? Like recently you touched on LangChain in the talk. It's probably one of the most common open source frameworks that are out there.
I think for most such systems, and not Alangji specifically, the hardest thing is architecture. So if you're building a connector between all kinds of different systems, then you have to like constantly refactor your code base end to end, which is very hard to do when you have a lot of contributors and people depending on your technology, which is going to be like a very hard thing to do. So I've rewritten every single library that I've ever written many, many times. So you only get better by iterating. And the faster you can iterate, the more likely you are to end up with the perfect design. And because AI and AI infra is advancing so fast, I'm not even sure that this perfect design for this connector exists. I'm not sure if OpenAI has something that's well designed. I'm not sure if anyone else has something that's well designed because like next year, the models will probably look different. And the constraints that we have in mind today will not apply anymore. So the big two topics that are probably worth discussing in this narrative is A, multimodality, and B, agents. And if multimodality, at least to me, is somewhat understandable, we've been working exclusively on multimodal models. So we approximately understand what the bottlenecks will be, what kind of information is coming in, what's coming out, how many inputs, how many outputs, like how to connect it with other systems, what kind of systems would people prefer to connect to. Then agents is like complete black box. Around Bay Area, everyone is talking about it. Every single founder, okay, half of them are working on agent-based programs, but there is so much variability in like how this can work and what it can look like that none of the systems for architecting a collection of agents can't even hope to be mature at this point.
You mentioned the bottlenecks of multimodality, like you're very deep in this area right now. What are some high level things that most people don't think about when it comes to building with multimodal applications or multimodal infrastructure?
There are a number of things. Like people still disagree with me on this, but I think the quality of alignment between multimodal towers of the same transformer, large multi-transform architecture, is very poor. So the way I tested it, I wrote an article that has a very long paragraph on this topic. The article is called Combinatorial Stable Marriages for Semantic Joins or something like this. So super obscure, a bag of words thing. But in there, there's part about multimodality. And what I did, I took open clip models, the largest ones there are, much larger than our models. So you would think their expressive capacity and understanding of multimodal content would be the best. And what I did, I sent images and text through different towers of this transformer, getting an embedding for the image and embedding for the text, and then trying to align and match two large collections of image embeddings and text embeddings between each other, reconstructing pairs, kind of trying to recouple them together. And that's where stable marriages come in. Stable marriages is this concept from economics. In 2012, there was a Nobel Prize for this. It's a fairly simple algorithm for you to match two collections of entities. So I've applied this and I've noticed that if I do this on multimodal content, even with very large models, the quality of matching and reconstructing the pairs is very low compared to like unimodal stuff. And what this essentially means for the end user, or even for AI researchers working in the domain, the models that rely on models like OpenClip have a lot to learn in the upcoming years. The example would be any form of text to image generation. So like when you generate a text from image, you need some form of a feedback loop that says or helps the neural network understand if the resulting image is similar to the input text. And if the model that kind of evaluates this is not as accurate, your generative model will also not be very accurate. So by improving the quality of alignment of multimodal transformers, you are not only improving the quality of multimodal search, which is dear to my heart, but also any form of multimodal generation. So this is like one of those things that is like super non-intuitive. And looking at Midjourney and Stable Diffusion and all the amazing images they produce, I'm one of their big users, love their stuff. And it starts to feel like we've hit the plateau and there's no way to get better. But there's a lot of ways to get better. And this is just one of them.
That's really interesting. And Stable Diffusion, if I remember correctly, is trained on clip. Is that true? Like
I'm not the best person to answer in terms of what exactly they use today. So
Yeah.
I would expect anyone doing multi-transformer stuff to be mostly using contrastive losses. And this is a testament to the fact that the industry was probably too focused on unimodal stuff the last couple of years. And except for Clip, which was pioneered by OpenAI, very few other approaches were suggested. So there was a paper by Salesforce that was inspirational to our work as well, called ALBF, that explores alternatives to training clip-like models. In our case, the idea was like to use a much smaller data set of much higher quality and also a lot more pre-training objectives. But in general, most people just use contrastive laws and a very large training pool to get to good multimodal understanding. So probably everyone uses the same thing.
Interesting. And then the difference in quality that you may have seen last year between Midjourney and Stable Diffusion was just training set, curation of good training data.
Might be the case.
Possibly, yeah. Interesting.
A lot of your work now makes things either faster, better, or allows you to do things with less memory. What do you think the implications of this are going forward, both for researchers, people building applications, or even people building infrastructure?
So I think the implications are on two ends. And so the most obvious one, if you are more efficient, you can do the same with less. You process a terabyte of data, you pay for your server 10 grand a month. How about paying 20% of that, or only 10% of that, and still processing the same volume of data with the same latency, which is definitely exciting and is more kind of on the cost cutting side of things. Of course, in today's economy, a lot of big companies are interested in this. They're saying, oh, our cloud bill is like unreasonable. We want to see what kind of technologies we can replace so that we can be more efficient. And here, our open source stack just comes in perfectly. It's fairly simple to use. So it's maybe not an end polished product like some of the other companies are doing, but it's free. It's entirely free. And it's also some of the most efficient software ever written. I'm more excited about the other end of things. So you still pay the same amount of money for your hardware. How much bigger can you go? Okay, so like you're processing a terabyte. Can you process 10, 100? Where does it end? So this is kind of the spirit with which a big part of the project was growing the first few years. I always dreamt about processing Google scale data sets. I didn't have Google scale money and not even a data center. So at first, I only tried to process everything on a laptop, which essentially meant being able to use vast pools of external memory, like SSDs, and design algorithms that actually work with this external memory efficiently. The implications today for this kind of stuff would be that I can take a server, let's say a beefy one, that has a terabyte of RAM. And you may say, oh, a terabyte of RAM is like super expensive. Ash, what are you doing? I mean, save your money, go buy some blueberries. But in reality, aside from a terabyte of RAM, I may also end up putting 200, 300 terabytes of SSD storage or a petabyte. So by my estimates, like today, the most I can fit into a single unit server is a petabyte, which roughly equates to 40 petabytes of addressable memory within a single rack. And a single rack is not really that much of electricity to be wasted. So with this kind of systems, you can build databases that can scale to Google scale and beyond with truly a fraction of resources. And that's kind of the direction I'm taking right now.
Interesting. When you say a fraction, what do you have any estimates? Have you run any math on that?
Oh yeah. You know those estimates for the number of advanced civilizations in the universe? I keep forgetting the name of this formula. I think it's a super vague formula with a few coefficients, mostly like multiplicative factors combined together. Like it's about as inaccurate as it gets. Now I can provide you a number of such inaccurate guesses compared to Google. I would need like a better knowledge of like how they do it to say like how much more efficient we are. But I kind of understand like how much data we can process within a couple of racks. And the number is just insane. So I'll be open sourcing more technologies related to this and releasing a few articles and benchmarks in the next few weeks. So if you stay tuned, you'll definitely find them interesting.
Very cool.
And now that you've unlocked this capability, what are some interesting things that you think people will do with this now that you can just do so much more with so much less?
It's a good question, but I'm not sure I have the right answer. So the right answer would include every single combination. You know, in math, if you ask someone what's like the solution to this equation and they provide you only one solution, but the right answer is a family of solutions, and then you're still wrong because like you haven't included every possibility. And the fact that we probably all agree on is that a testament of a really good technology is seeing people use it in the ways that you don't expect. I'm happy to have experienced this a few times in the last few years and makes me really excited. Some of the obvious things that we've discussed, and I guess we also discussed it with a bunch of guys at Founders Inc., is like the kinds of even user interfaces that can be unlocked. And in here, we're talking about like super low level stuff and super high level stuff as well. So let's start with the super low level. Some of my libraries are built in such a way they don't even have libc as a dependency. So this is essentially the most fundamental dependency of every single package out there. And my libraries don't have it. So essentially they're built in such a way that you can build a bootable system without even including libc. So there's no operating system involved at all. So you're just booting your machine, and the first thing you see is the stuff that's built on Unum's technology. And there's absolutely minimum amount of code used there. So you end up with an operating system image that is like a few megabytes in size, but it has all the most advanced data processing capabilities ever designed. That's super low level. What about super high level? So there's been like crowd vector search technologies this year. Hardly anyone actually like cares this much about performance, which is fine. Not everyone needs it. Or let's say portability to every single platform, which again, not everyone needs it. But I'm also excited about being able to provide people with functionality that can be unlocked with the same data structure. What I mean is that once you build the index, which usearch, the vector search engine, allows you to do it to perform k-approximate nearest neighbor search in like high dimensional space with a lot of different points, you think, okay, I'm going to use it for search. But once you have the index structure, you can kind of unlock more possibilities and like opportunities from the same structure itself. So one use case that I had in mind, and this dates back to 2015 and 2016, and us gathering with friends, not even here in the US, but somewhere in Hong Kong. A cool story for another day. But we've been chatting about the kinds of user interfaces that can come up in VR and in 3D, like once the technology is advanced enough, all the all the typical speculations. You can imagine those. But one of the aspects was like, how different would the layout of user interfaces be? Like today, we're used to those scrolling lists on iPhone and maybe grids at the best if the developer wasn't too lazy. But if you are not constrained by a tiny two-dimensional piece of glass, what else can you unlock? Like, how do you organize all the information around the person so that you can kind of track his movement? You can kind of highlight content around him. So like you have a lot more space and you have more dimensions. That's the most you can ask for like new forms of user interfaces. So I was very excited back then and to build like things such as clustering. And now I have them in usearch as well, which once the index is constructed, allow you to highlight clusters so that you can draw a cluster of information somewhere and then iteratively kind of dive into that cluster and then split into clusters, the parts of that bigger cluster. So if you use conventional tools, most of the time you have to recompute the clustering itself. Moreover, like those systems, they scale very poorly. If you want them to be fast, you run them on the GPU. GPU memory is scarce. You cannot fit billion point data sets there. I was just reading one of the papers from an unnamed GPU company that suggests an algorithm for a vector search. And the original study was limited to 100 million vectors. Today, I work with close to 30 billion vectors on one machine. So this is like, how many? 300x gap in scale within the same single node and comparable energy consumption. So if you can cluster this many points and you are not even constrained by them being vectors, those can be any points. What else can you build? So my system allows you to define custom similarity metrics. So it's similar to databases, which have this concept of user-defined functions. Our vector search engine has like user-defined similarity metrics. And you can essentially throw anything you want in there, define a similarity metric for those two objects, be it like 3D structures, be it protein structures, molecules, physics interactions, textbooks, strings, you name it. And then cluster tens of billions of points on every single machine, kind of helping you uncover the relationship between different objects. So the possibilities are endless, both on the user interface design side for product companies building on this kind of tech, but also for scientific research, which I'm personally very excited about.
Really what you're saying is time will tell, right? There's so many different things that this technology can be used for, and we might just have to kind of wait and see. What would you tell somebody who was maybe interested in this sort of technology and interested in learning more about it? I think a lot of our audience is more working at the application layer with AI right now, maybe training their own models, but not working at as deep of a level as what's going on in Unum. To people who want to learn more about usearch and maybe use it for, clustering some vectors or experimenting, how should they get started? What's the first step they should take?
So the first step for data scientists and let's say people in the more AI crowds, for my projects is like super simple. It's just pip install. So most of the projects are simple and short enough so that the core starting guide fits into the first README file of the project. So like all of the core functionality is essentially in a single textual file that you can read within a few minutes and understand what the library is capable of. But extrapolating and going to other projects and just systems thinking in general, I think there is a lot of missed potential in modern AI where people just use very high level tools like PyTorch, for example, and rarely try implementing their own custom layers, for example. So if they do not implement the custom layer, they're only limited to the primitives they have, which kind of limits their creativity in terms of what kind of architectures they want to try next. And the problem there is that the entry barrier from high level Python stuff to low level compilers and kernels and CUDA it's a huge gap. So I was just writing an article about how we ported one library to 10 programming languages. And one section there is what would be an interesting entry point for a Python developer to understand low-level systems better. And there is this project that almost no one knows about called CPPYY, which is based on Cling. And Cling is a physics project, essentially. It's like a way of using the Clang compiler for C and C++, but for just-in-time compilation so that you can use C++ in Jupyter notebooks, essentially. So physicists were processing a lot of data. They couldn't use Python for this. So they took the C++ compiler and then transformed it into a JIT compiler. And then someone else wrote a project, a wrapper around it called CPPYY. It allows you to define C++ sections of code within your Python application so that you don't have to learn all of the complex C++ tooling. You can start by implementing a single function in C++ and go from there. And in a similar spirit, NVIDIA has those amazing Rapids libraries. Probably some of the most amazing libraries that are the least known. I gave a few lectures on those in the last couple of years, and I'm still surprised people didn't know about this. But if you have a GPU in your machine and you're still using Pandas, NumPy, and NetworkX, you're losing a lot of money right there. Because you could have just replaced the import statement from Pandas to QDF, from NetworkX to QGraph, and from NumPy to QPy, and all of the same operations would run on the GPU. And there's a lot of clever engineering that's going into implementing a portable and actually working solution for the same Python functionality, but on the GPU. The least known part is that QPy also has some hidden gems, including a way for you to compile CUDA kernels on the Python side and set it to the GPU. So this way, we're not only doing combining C++ with Python on one end for the CPU side with CPPYY, but you're also doing a combination of CUDA and Python also within the same file, which is super handy. And of course, if you check out some of our libraries, we have a lot of stuff covered on this topic and how to integrate this functionality and get GPU acceleration as well.
Awesome. Very cool.
I think, Ash, we're out of time. Thank you so much for coming on. Where can people find you online?
Oh, it's super simple. My nickname is the same on essentially every single social platform. So it's literally my name, Ash, and then the last name, Vardanian. So LinkedIn, Twitter, GitHub, most importantly, GitHub. Find me there and find a bug. Tell me about it. I mean, you can find me on Discord and tell me, Ash, you liar, we trusted you. The system has a bug. Please fix this. I'd be happy to help. We have a very cool, interesting environment there.
Awesome. And what's one thing that you would like to leave the audience with?
I want everyone to be hackers in the best sense possible. So when you have a system and you build it, it's amazing. When you've built something on top of somebody's also system, it's also amazing. But finding ways how to abuse technology for something it's never been used for before is amazing. It really uncovers new use cases. And I'm most excited about these kinds of people and this kinds of applications. So go home and hack something, break somebody else's system. It will be exciting experience both for you and the person who designed the system in the first place.
Incredible.
I love
And
that.
for people watching this on YouTube, comment below if you've hacked a system for a use case that it's not intended for. I'm excited to see what people have done in the past. And once again, Ash, thank you so much for coming on. It's been a pleasure.
The pleasure been mine.